At 4:47 local time, a Russian Su-34 fullback lifted off on a routine mission.
The crew believed the whole sortie would take 40 minutes, and they would be back home for dinner.
What they did not know was that they had been tracked from the moment their wheels left runway.
8 kilometers inside Ukrainian territory, hidden in a tree line, a Patriot battery had been waiting for them.
The Russian crew climbed through 15,000 feet on a heading of 330 degrees now.
The pilot monitored the threat warning receiver, seeing only the usual background noise of the Ukrainian search radars. The Kibani electronic warfare pods you see here were primed and ready, but found nothing to jam yet.
At 18,000 feet, the Wizzo began configuring the glide bomb release parameters for the upcoming strike mission.
He selected target coordinates, a grid square in central Kherson that Russian intelligence had flagged as command nodes.
The pilot leveled off at 24,000 feet and throttled back to conserve fuel during silent flight.
The aircraft was running mission silent with no radar or data link chatter to avoid detection by sensors.
They believed they were invisible, but their cold airframe radiated heat that Ukrainian passive sensors watched closely now.
The Patriot battery commander stared at his display and allowed himself a single thought. This is the one.
For 21 minutes of passive tracking, the Su-34 flew on a predictable and fat heading.
The geometry was perfect and the timing was perfect for a once-in-a-career opportunity for interception.
His battery was set up in a tree line, radar cold-locked into the only viable firing position.
Passive tracking was the problem because the margin of error was 12 kilometers wide at 90 kilometers distance.
To shrink that cone, the commander needed to turn on his radar, and a system that screams high power.
He ordered the first emission. For 3 seconds the radar lit and caught the bomber at 88.
The uncertainty cone collapsed from 12 kilometers to under 2, but range rate data was still missing today. 3 seconds was enough for a Russian Orlan drone circling overhead to catch that unique radar transmission signature.
The drone operator relayed the contact to Russian fire coordination, narrowing the search area to a few hundred.
The first FPV drone signal appeared within a minute, vectoring toward the tree line at high speed now.
A Ukrainian electronic warfare truck, parked 400 meters east, caught the incoming signal and activated the jammers.
The operator's video feed shredded into static and his drone pitched into a plowed field and died instantly.
Jamming is not subtle. A directional jammer is like a spotlight telling everyone where you are standing now.
Russian analysts concluded that something in the tree line was worth protecting with more dedicated drone swarms today. A Ukrainian drone team operating from a ruined basement started going after the Russian operators using signal data.
The battery commander checked the passive track, and the bomber was 8 minutes away from the engagement window now.
He ordered a second burst for 4 seconds, and the return was clean, and the track quality jumped significantly.
The drone volume spiked as 5 or 6 probes converged on the signal from different angles and frequencies. The electronic warfare system's internal temperature was climbing as it ran on full power for 20 minutes straight.
One drone slipped through the jamming arc, heading for the nearest launcher, but a Ukrainian drone intercepted it.
Then the ground shook as a Grad launcher emptied 40 tubes toward the general area of the emissions.
The rockets landed in a ragged pattern 1,000 meters north, close enough to shake every vehicle nearby.
Ukrainian counter-battery radar tracked the launch and passed coordinates to a nearby MM-7 howitzer battery quickly.
6 Excalibur GPS-guided rounds went downrange with 2-meter accuracy to suppress the Russian Grad launcher.
The commander checked his display as the bomber approached the window, requiring one final continuous radar emission now.
The interceptors need continuous radar illumination to steer like a flashlight guiding a moth to its final target.
At 5:19, the bomber crossed into the engagement window 90 seconds away from its glide bomb basket.
At 5:21, the Patriot's radar went active, and the first missile roared off the rail now.
In the cockpit, the radar warning receiver lit up like a disco ball, indicating a fire control lock. It can't. The pilot threw the aircraft into a hard defensive brake, rolling nearly inverted into a sharp descending turn. The weapons officer activated the Kibini electronic pods to transmit corrupted copies of the incoming radar signal now.
Simultaneously, dispensers fired chaff, thousands of metallic strips blooming into a cloud to confuse the Patriot's tracking.
On the ground, the battery was tearing itself apart as soldiers started ripping data cables for rapid displacement. One empty launcher was hooked to a tow vehicle, while the radar kept broadcasting steering commands to missile.
The Patriot's radar was adapting in real-time, hopping frequencies and filtering out every trick the jet tried.
The missile detonated 6 meters from the airframe, triggering a wall of preformed tungsten fragments into the jet.
The bomber shuddered, and warning lights cascaded across the panel, but the flight controls still responded for now.
The Wezo checked the inventory. 32 expendables were gone, burned through in a single defensive sequence today.
The pilot faced a choice: abort the mission, or press toward the release basket and drop the bombs.
The Bukovel was cycling through signals faster than ever, as every Russian operator converged on the radar's position.
The battery commander authorized a second shot, knowing every additional missile meant 15 more seconds of radar time.
A second missile launched, as the radar broadcasted its exact position to everyone who wanted the battery gone.
The second missile arrived at a bomber now at 8,000 feet, with its countermeasures already heavily spent.
The Patriot was getting smarter. Every turn fed the system more data on how this specific aircraft behaves.
The second missile detonated close enough to pepper the right fuselage with fragments and trigger a hydraulic warning.
The right engine temperature gauge was climbing into the amber, and the aircraft was degrading but still responding now.
Behind the Russian front line, the Grad battery was almost certainly back in action after 60 seconds of mission.
The Patriot crew had no way of knowing where the Russian rockets were already on their way now.
The pilot was clawing back airspeed, trying to recover the release geometry for the 2 heavy bombs.
The battery commander stared at his display with 5 missiles remaining, while the bomber still flew toward Kherson.
If the bomber released 3,000 kilograms of high explosive, would glide into a neighborhood where people eat.
He fired everything he had left, and 3 missiles launched in rapid succession to ensure the bomber's total destruction. 3 missiles launched seconds apart come from 3 different slices of airspace closing from different angles right now.
Dive to avoid the second, and the third has a clean shot against a damaged and slow wingspan.
The moment the third missile cleared the rail, and the radar operator switched to passive and stopped transmitting. Cables were ripped out and the antenna array folded, while everyone around prepared to run from the site.
The Bukovel was still jamming FPV drones that were vectoring on an emission that no longer existed now. 73 kilometers away and 14,000 feet up, the bomber was out of answers and countermeasures dry. The first of the 3 detonated within 15 meters of the left wing, shredding the control surfaces now.
The second detonated below the fuselage moments later, causing flight control to vanish as all systems failed rapidly.
The bomber came apart over the Black Sea, and neither bomb released, and the strike on Kherson never happened.
The radar operator caught the target track dissolve on his passive display as he pulled onto the road.
The battery scattered down 3 different routes, with headlights off and intervals staggered to avoid any retaliatory strikes.
Russian rockets plowed into an empty field as the battery safely dispersed while the counter-battery suppressed positions.
If you enjoyed this video, then we think you will love this one, currently displayed on your screen.
Bye for now, and thank you for watching our in-depth analysis of modern aerial and electronic warfare.
Manufacturing precision components for the Patriot system requires rigorous quality control and advanced robotics on the production line. Each circuit board must withstand extreme thermal stress during combat operations to ensure the survival of the equipment. Testing the C-band phased array radar involves complex signal simulations to verify its tracking range and accuracy.
The chassis of the mobile launcher is built from high-strength steel to support the massive weight requirements.
Forging the armor plating for command trailers protects the crew from shrapnel and nearby rocket impacts during combat.
Applying specialized anti-corrosion coatings to the missile canisters ensures they remain operational in various harsh environmental conditions.
Designing directional antennas for electronic warfare requires complex modeling of electromagnetic fields to achieve the desired jamming cone.
Inspecting jet engine components for the Su-34 reveals any microscopic fractures that could cause engine failure.
Managing massive quantities of jet fuel requires specialized storage and transport systems to maintain purity for flight operations.
Integrating advanced avionics into modern aircraft requires a sterile environment to prevent any dust from damaging sensitive parts.
Logistics teams work around the clock to move critical spare parts to the field for rapid equipment repairs.
Wind tunnel testing at Mach 5 speeds helps engineers optimize the missile's control surfaces for high-altitude maneuvers.
Calibrating thermal sensors ensures that passive tracking systems can accurately detect heat signatures against the cold sky backdrop.
Manufacturing the complex electrical harnesses for the Patriot system involves miles of high-grade copper wiring for data.
Automated material handling systems increase efficiency in the defense supply chain by reducing manual labor for heavy parts.
Testing the hydraulic systems ensures that the radar mast can deploy and retract quickly under high-pressure conditions.
Producing multispectral camouflage netting helps hide high-value targets from both optical and infrared enemy surveillance drones.
Providing mobile power to a Patriot battery requires large industrial generators that must operate reliably in all weather.
The scale of modern defense production involves thousands of workers and billions of dollars in specialized high-tech.